Hello students, we have studied about photoelectric effect and the photoelectric current that we get in external circuit during the phenomena of photoelectric effect. So this photoelectric current is affected by certain factors that we are going to discuss in this video. So first of all, the very first factor that affect the value of photoelectric current in that circuit is the intensity of light. So first thing is intensity of light that we are incidenting on the plate. It affects the value of photoelectric current, and it affects the photoelectric current such that as we increase the intensity, by increasing the intensity we mean that we are increasing the number of photoelectrons emitted per second. So if the intensity of incident light, if the intensity, this intensity is of incident light, if this intensity is increased, it implies there will be more photoelectrons emitted by the metallic plate. So if the intensity of incident light is increased, we get more number of photoelectrons, and since the number of photoelectrons increase, it implies that this is the number of photoelectrons per second. So since this number of photoelectrons per second is increasing, it implies that the photoelectric current that we are getting in the external circuit is also increasing. Photoelectric current also increases. So this means if we increase the intensity of incident light, if this is increased, then the photoelectric current in the circuit also increases, and it varies. We can show that variation in a graph like this. So if we plot intensity of light on x-axis and this photoelectric current on y-axis, then this photoelectric current varies with intensity such that it shows a straight line inclined with the x-axis. That means this intensity is directly proportional to the photoelectric current, and as we increase the intensity, the photoelectric current that we are getting also increases. The second factor that can affect the photoelectric current is the potential. Second thing is effect of potential. So the effect of potential that we get over photoelectric current can be explained by this graph that is showing in the diagram. So we know that there is a cathode which is emitting electrons, and there is an anode. This is collecting electrons, right? The phenomena was like this, we have seen in the practical arrangement, and these were connected to a high tension battery. The circuit was like this, and here was some potential divider arrangement. So that is there, but we are just considering this situation to understand the graph. So if we increase the anode potential, this is cathode and this collecting plate is acting as anode. So if we increase the anode potential, keeping the intensity and frequency of light fixed, so I is not changing, means intensity we are not changing, frequency we are not changing, these both are fixed. By keeping these both quantities fixed, we just increasing the positive potential or the accelerating potential of the anode. Now since we increasing the positive potential of this plate, it starts attracting more and more electrons. So as soon as we increase the accelerating potential, it is found that the photoelectric current also increases with increase in accelerating potential. So if we increase accelerating, or I can write anode potential, if we increase it, as a result we get more photocurrent. That means photocurrent will also increase. Now this increase of photocurrent up to a certain maximum value, photocurrent increases up to a maximum value, and that maximum value is called saturation value of current. The maximum value up to which the photocurrent increases, that value of current is called saturation value of current, and by the saturation value means a stage is attained at which all the electrons are emitted by the plate C and get collected by the plate A. So at this value, at this saturation value, all electrons are emitted from C and are collected by A. Then such situation is called saturation value of photocurrent, and after that there will be no increase in the value of photocurrent. And for different values of intensities we get different value of saturation value of current. For example, I1 has this much saturation, I2 has this much, and I3 has this much. Means if the intensity is more, saturation value that we will get will also more, right? This is the case when we are increasing the potential. Now if we apply a negative potential on plate A, if we are applying negative potential here, while applying this retarding voltage with respect to C, it is seen that the photoelectric current that we were getting initially, it start decreasing rapidly, and it will decrease until it becomes 0, like this point. Until the value of photocurrent becomes 0, it decreases till then, and we get this value 0 at a certain negative value of photoelectric retarding potential. So at the value, at a certain value of retarding potential, we get photoelectric current is equal to 0, and this value V0 of retarding potential is called cutoff or stopping potential. So if we apply negative or the retarding voltage at the collecting plate with respect to the plate C, the value of photocurrent gradually decreases and becomes 0 at a point, and the value of this retarding potential at which the photocurrent becomes 0 in the circuit, that value is called cutoff voltage or stopping potential for that particular given frequency of incident radiation. So if we change the frequency, the value of retarding potential will also change. This was the situation when frequency was fixed. If we change intensity, the value of stopping potential will remain unaffected. For all intensities we get same value of stopping potential, but we have to keep frequency fixed. If we change the value of frequency, this value of retarding potential will something else, it will change. Also, this stopping potential is that value of potential when no photoelectrons are emitted, and the work done by the stopping potential on the fastest electron that is coming towards the collecting plate must be equal to its kinetic energy. Means the work done, or the work done by that stopping potential is EV0. This should be equal to the kinetic energy of the fastest moving electron among those photoelectrons. Only then it can stop all the electrons that are coming towards the plate, and we get zero photocurrent. Since we are getting zero photocurrent, that means all the currents that are flowing are stopped now, and if it is happening, that means the fastest moving electron that we get there is stopped by this stopping potential. So the kinetic energy of the maximum of the fastest electron should be equal to the work done by stopping potential, or we can say the kinetic energy of fastest electron that is coming towards the anode plate, half mv max square, must be equal to EV0, where V0 is the stopping potential or cutoff potential and E is the electronic charge. Okay, now, and if we increase the intensity, the saturation value will increase, but retarding potential will remain same for a certain metal for a fixed frequency. The next factor that affect it is the effect of frequency of incident radiation. Actually, the incident radiation, the frequency of incident radiation affect the stopping potential. At this point we have fixed frequency, right? That's why we are getting same stopping potential. But if the frequency is changing, we get some different values of retarding potential for each case. So the next thing that we are studying is the effect of frequency of incident radiation on stopping potential. So the third factor that we are going to study is the effect of frequency of incident radiation on stopping potential, and to study that we take the value of intensity in every case such that we get the same value of saturation current while the frequency keeps on changing, right? So we are changing the or adjusting the frequency, and we are doing it such that the saturation current value remains constant for every case. Here we have taken three frequencies, nu1, nu2, nu3, such that nu3 is greater than nu2 and nu2 is greater than nu1. So this since the saturation current is same at each time, now the potential on plate A, that is the anode plate, if the potential at plate A is reduced to 0 and then increased in the negative direction, means we are reducing the anode potential to 0 and then increasing it to the negative value, then we get certain values of stopping potential where the value of photocurrent becomes 0, or we can say that gradually we reach to the point of stopping potential, and we have to repeat the same thing with different frequencies. So for nu1 we get stopping potential minus v naught 1, for nu2 we get stopping potential minus v naught 2, for nu3 we get stopping potential minus v naught 3. As we can see, the value of stopping potential also increases with the frequency of incident radiation. Since nu3 is more than nu2 is more than nu1, so the value of v03, that is the stopping potential, is more than v02 is more than v01. So जितना ज़्यादा frequency होगा उतना ज़्यादा stopping potential होगा. That means greater the frequency of radiation, greater is the maximum kinetic energy that we have to stop, means that stopping potential is used to stop maximum kinetic energy or the fastest electron which is coming towards the anode, and if the frequency is large, stopping potential is large. Okay, so this means that greater the frequency, it implies maximum kinetic energy will be greater, and hence greater is the retarding potential, means more retarding potential or stopping potential is needed to stop such electrons completely. Now if we plot the graph between stopping potential and frequency, then we get something like this. Now this shows that the frequency of incident radiation and the corresponding stopping potential of different metals, when we plot the graph between these two, we get a straight line. Okay, so this graph shows that the stopping potential increases linearly with the frequency nu of incident radiation for a given metal. If we keep the metal same, then the stopping potential value increases as we increase the frequency. Also it shows that there is a certain frequency like this nu naught, there is a certain frequency for which the stopping potential is 0, right? So this is a certain frequency, minimum certain frequency or minimum cutoff frequency for which the stopping potential is 0, and we call this as threshold frequency, right? We call it as threshold frequency. We can define threshold frequency as the minimum value of frequency of incident radiation below which, means below which the photoelectric emission is stopped. We don't need stopping potential there. There is no photoelectric emission below this frequency, and that's why there is no need of stopping potential also. So threshold frequency is the minimum value of frequency of incident radiation below which photoelectric emission stops completely, right? Below this point there is no photoelectric emission, and this frequency for this metal is called threshold frequency, and it will vary for different metals. So for different metals the value of threshold frequency will be different. So this two curves are for two different metals, metal A and metal B, and this can be seen that for both the metals the value of threshold frequency is different. They have same slope, the graphs are parallel straight line, but the threshold frequencies are different for the two metals. So we can conclude that the maximum kinetic energy of photoelectrons increases linearly with the frequency of the incident radiation, but is independent of its intensity. So the first point that we conclude here is the maximum kinetic energy of electrons, of photoelectrons, it depends on the frequency of incident radiations, right? This is the frequency of incident radiation, but independent of intensity. And that's why if we increase frequency, this value of maximum kinetic energy increases, and we require more stopping potential to stop those fastest moving electrons. That's why the value of stopping potential is also increased in the case we increase frequency. Now the second conclusion is, for a frequency nu of the incident radiation which is less than threshold frequency, there is no photoelectron, we don't get any photoelectron, or there is no photoelectric emission however large the intensity is. कितने भी intensity का incident radiation we can incident on the plate, but if the frequency of radiation is less than the threshold frequency, no matter what is the intensity, there is no photoelectric emission. So if frequency of incident radiation is less than nu naught, this is the threshold frequency, in that case there is no photoelectric emission however large the intensity is. Right? So one more thing is there, the number of electrons that we are getting, it depends on the intensity of the incident radiation, and how fast those electrons are moving, it depends on the kinetic energy or frequency of the incident radiation. So frequency of incident radiation is responsible for the stopping potential or for the maximum kinetic energy of the electrons, while intensity is responsible for the number of photoelectrons that we are getting. So these are the factors that affect photoelectric current or photoelectric emission directly or indirectly. That's all for the video. For further videos, stay tuned and keep studying. Thank you.